Good morning, everyone. So this is Modeling Analysis Lab. So code is 17 ME 16A. So this lab is categorized into three parts. That is Part A, Part B, and Part C. In Part A, we will learn about different bars with different cross sections. So such as uniform bar with the same cross section and taper cross section as well as the stepper bar with the different material as well as the cross section. Then we look into the different process problems. Okay, so generally he has given minimum two exercises of different types that will solve in the same thing. Then beams, the simply supported cantilever beam with a point load, UDL beam with a varying load, etc. So these kind of problems will solve by using our ANSYS software. Then again part A we have one more experiment, that is stress analysis of a rectangle plate with its circular one. Here we will generally find out the stresses at the particular hole. Okay. Then in part B we have the thermal analysis, that is 1D 2D problem with conduction and convection boundary condition. The same kind of problems where we have solved in the classes or online classes, same problem is solved by using ANSYS software. Then we solve some dynamic analysis to find, that is dynamic concentration. There we have solved some eigenvalue to determine the eigenvalue and eigenvector. So same thing, same problem we solve using two problems we solve of, of this dynamic analysis. Okay. Then part C we have the only demonstration, that is demonstrate the use of graphic standard, IGS step, etc. to import the model from the model to solve the. That means if we have the CAD model software, so how that model can be input into ANSYS. So which kind of extension we have to use when we input the model from the modeling software into the analysis software. Okay, so that is IGS and step that we also do in the subsequent process. Then we have demonstrated one example of contact analysis to learn the procedure to carry out contact analysis. So that will also solve the problem. Then we demonstrate at least two different types of example to model and analyze bars for a plate made from composite materials. Okay, so these are the experiments we need to complete in this lab, that is modeling and analysis lab. Right. So now we move on to the first problem, that is part A, which is nothing but your bars of a constant cross section. That is nothing but your uniform bar problem. So here you can see. So yeah. So what's the aim of this experiment? Here we need to determine the nodal displacement, that is displacement at each node, as such as in each element, and reaction at the subgroup. So here you can see that we have one bar at the at one end is fixed and other end is nothing but it's having some kind of force. Okay, so equal to 10 kilonewton here given, and the material of this bar, that is length modulus, is given at 200 gigapascal, and area of cross section of the bar is 10 to the power of 4 mm square, and length of the bar is 1000 mm. So before we proceed into the ANSYS, just to make sure that all the dimensions must be in mm or Newton. Okay, then we already know how to solve this problem by using our theoretical method. That is, we have to follow some FEA steps. But when we solve any problem into ANSYS software, again we have to follow the same steps, but in different phases. So in ANSYS, we have three phases. One is preprocessor, solution, and general post-processor. So generally, uh, preprocessor is nothing but in which the analyst develop a finite element mesh, that is discretization, to divide the given geometry into subdomain for mathematical analysis and apply the material property and boundary conditions as well as the load. Okay, so it's nothing but deck preparation is generally called when we do the modeling. So that kind of process we generally call deck process. Okay, deck preparation. Then the next phase is solution. In that solution, during which the program derives the governing metric equation from the model and solve the primary quantities. And okay, that means whatever given the input, so before the date preparation, that we will solve in the using the solution. Then we have this general post process. In general post processor, we generally in which the analytic checks the validity of in the solution. Okay, then examines the values of the primary quantities such as displacements, meaning and stresses, and derive and examine the additional quantities such as specialized stresses, error indicators that we can see, and also we can view the result, we can draw the graph. Okay, so etc. All the things can come into this standard processor. Now let's see first problem how to solve. So this is the name of experiment 3. Now I'm using this ANSYS 17.2. So there right now, if you open your ANSYS website, there we see the ANSYS 20 is going on. Okay, so, so one more thing I want to tell you before I process this problem. So below this ANSYS 17.2, the real constant, here you can see that the real constant is generally used to define the area. But above this 16 version, they will make changes. That is real constant. Now here we can't do any, can't define the area. So for that, what we have to do, we have to go to the section. There we have to define your area. Okay, let's see how. First, before I start this problem, first create a job name. So here, okay, so create one more new file, fine. Then file with the same job name, just write as experiment one. Okay, so next. Then you can change the directory, save file option, means save location. You can save anywhere in the system or laptop. So you can, if you click on the change directory, you can change the save location. Then go to the change directory. So what kind of problem we are solving? We are solving uniform bar problem. So so here we have a uniform. Okay. So this problem is looking at a uniform bar problem. Save. Now here what you have to do is just click, right click your mouse and click on the fit. So here it will appear, that is uniform bar. Now first step in this analysis, go to the preference, click structure because we are solving the structure. Then go to the preprocessor. Now we are preparing our model. Go to the element type. So whatever we have the problem, so we have converted into this 1D. So we can convert 1D, 2D, 3D. Okay. So right now we are solving by using 1D agent. So here, put the add edit, go to the add, go to the link, save. Next. Then here I said real constant is mainly for to define our area. But in the 17.2 we cannot define our area by using this real constant. So let's see how to define the area. Then go to the material property, select the material models, select structural, linear, elastic, isotropic. So here we assume that the material, whatever is in the part is same. Okay. So that's why we are taking isotropic material. So here the Young's model is 200 gigapascal. So you have to convert this 200 gigapascal into 400, sorry, into Newton per meter square. So for that, it is 200 E. Here into is nothing but E power raised to 3. So this is nothing but Newton per mm square. And in problem, if it's not, Poisson pressure is not given, so just take 0.3. Select and this goes the material models. So now we have created our material. Now go to the next modeling or go to the first section where in that section we can easily create our area of this bar. Okay, so right now we have only one bar or one element, that's why we're creating only one ID. Then here you have to give the area. Here you can say section data, linked area. So what's the linked area? You can see here. The area is 10 to the power of 4 mm square. So here you can write 10 e to the power of 4. See 4. Now I have created my area also. Now I have to create my model. So when you are creating a model, so we can create by two methods. One, we can use key points and lines, or nodes and elements. So if I use my key points and lines, that is the thing that I'm using for geometry. For that we need to mesh once again. But if I use nodes and elements, so we need not to mesh once again. So right now we are using the nodes and elements. So for that, just click on the nodes, click on the inactive coordinates, right? One, that is node number one, x equal to 0, y equal to 0, z equal to 0. Say apply. Now just go to your problem, see what is the length of this bar, that is 1000 mm. So here write as second node and write as 6000 and see OK. So here you can see that we have created the two nodes. So one node at this point and second node at this point. Now, once we created the node, next step is to create the element by using these two nodes. So go to the element, go to the auto node, and click on the throw nodes. Just click on the first node, click on the second node, and say OK. So it will create the element. Now, once we have the element, next what you have to do is to apply the boundary conditions. That is nothing but your load constraints. Okay. Then go to the node, go to the define nodes, go to the apply, go to the structural, and in this problem, at one end, that is at node 1, it's a fix, and at node 2, we have force, which is in positive direction, that is tension. Okay. So just go to the to constrain this node, go to the structural, then click on the displacement. In that, just click on nodes because we are using nodes as well as the elements. So let's click on the nodes, click on the node one, say OK, and constrain all degree of freedom. Select all degree of freedom and say OK. Okay. So this constraint your node one. Now to apply the force, once again you have to go to the nodes, then go to the define node, click on the apply, go to the structural, then click on the force moments. In that also you have to click on the nodes. Just click on node 2 because if you see your problem at node 2 we have force. So here click on the nodes 2, say OK. Now what is the value of force here? 10 kilonewton. So and it's in positive direction. Okay, so that is 10 into 3 into 10 power of 3. Okay, see, now I have created my there is geometry in AFL. That is described as a geometry. Okay, then so once we create a preprocessor, next step go to solution, go to the analysis type, and this is we call the new analysis. So we just cross check that check this is static or not. If it's static, then say okay, because we are doing static analysis. Then go to the solve, we call the current solution. So this will give you your solution. So once it says solution is done, I think the solution is finished. Then close all these things. Now we need to view our result. So what we need to determine here, we determine the nodal displacement, stresses in each element, and reaction to result. Okay. So what we have to do? First, go to the element table. Okay. So I do list of results. Let's go to the list result. In there, just click on the nodal solution. Go to the degree of solution, displacement by percent. Now we can see. So what we got 0.5 into 10 power 3. So if you see your deformation, that is your theoretical value, what we got that is 0.5 mm. So it's correct. When we go through this theoretical method, that is 0.5 into 10 power minus 3. Okay. So now, so next we need to come to the element solution. So here stresses, go to the bonus, click on OK. So here you can see that 0.1. So, fine. So 0.1 megapascal or 0.1 Newton per mm square. Okay. So reaction solution. So here you can see the reaction solution. Click on all items. So we can see we get the minus 1000. So why we are getting minus 1000 Newton means, so here we apply that load to positive direction first, that is 1000 Newton. To make this equilibrium, so obviously reaction force is opposite to your applied force. So that's why we are getting negative here. Okay. So here you can say we get negative line. Right? Now, how to convert this 1D element into 3D view? For that, you just keep this your 1D element into isometric view, then go to the plot controls. In that style, go to the size and shape. Then here you can see the display of element. Just click on and see OK. So this is nothing but your 3D view. Okay. Now, how to animate the deformation? For that, just go to the plot controls, go to the animation, then deform shape, click on the deform and undeform, and see. So this is nothing but deform shape. You can see normal is deformed. Right? So next, to close this deform or to close this animate, just click on the close. Let me stop your animation. Now, to know the stresses which is produced in this bar. So for that, so go to the element table, then click on the define table, go to the add. Here you just write your stress, then go down, click on this bisequence number, and click on this LS and write as 1. And see, so this will give you a stress value. Close. To view our stress value, go to your plot result, go to your contour plot, then element table, stress, say 50. So here you can see 0.1 Newton per mm square. Okay, and your deformation that is 0.05 Newton per 3. Fine. Okay, guys. Thank you.